This video addresses the question from the textbook for Chapter 6, number 42, where we're looking at comparison of an apartment rent to a mortgage. And what we see in the question is that it says San Mateo County in California published extensive descriptive statistics from its 1998 Quality of Life Survey. The county reported that the mean house payment, mortgage or rent, was $1,225.15, with a standard deviation of $777.50. It was also reported that the mean cost of an apartment rental, rather than a house rental or a mortgage, was $868.86. So for this exercise, treat the overall mean housing payment as a parameter. So if we treat this value as a parameter, then that means that it is going to be a mean mu. And the apartment rental cost is treated as a statistic. So we know that that has to be M. And we also know, according to the problem, it says based on a sample of 100. So we know that there are 100 people in the sample, or 100 apartment costs. So we know that's N. So that leaves us with, remember that we're saying that the mean house payment is this in the population. And so over here, this is going to be sigma, okay, because we're talking about the distribution of scores. Okay, so using symbolic notation, this is part A, and formula, determine the mean and the standard error for the distribution of means for the overall housing payment data. So we need to know the mean and the standard error for the distribution of means. So remember, when we're talking about a distribution of scores, then our population mean will be mu. When we're talking about a distribution of means, we're talking about a distribution of means where the mean is mu sub m. Now, what happens is that because the distribution of means is created by repeatedly sampling from the population of scores and then creating means, we actually find that mu is the same as mu sub m. So in this case, we can say, oh, well then mu is the same as mu sub m, and so therefore we already know that's $1,225.15. In order to get the standard error, however, we're going to have to do some transformation. So we do have the values that we need for the standard error right here. We have sigma, and we also have n. Okay, so we know sigma and we know n because the standard error of the distribution of means, sigma sub m, is sigma divided by the square root of n, which is the number of scores. So in this case, we have 777.5 divided by the square root of 100, which we know is going to be 777.5 divided by 10. Just move the decimal place, and we get 77.5. And that is our standard error. Okay. So for part B, what it's asking, it says using symbolic notation and the formula. So again, we're going to come back and use these symbols and find our formula. We're going to calculate the z statistic. Now remember that the z statistic is used when we are talking about making a comparison of a sample mean to a population mean. Okay, so because we're using a sample mean in our comparison, we're talking about using the distribution of means. not the distribution of scores. So that means our z-statistic uses the formula of the mean of the sample minus the mean of the population divided by the standard error. If we were talking about using a score, then we would actually be using this formula. Z equals the score minus mu over the standard deviation. Okay, but we're not doing that, so let me erase that real quick. Let's see. There we go. Let's get rid of this. Or maybe it won't let me. There we go. Just didn't like my angle there. And I'm actually going to erase this part so we have a little bit more room, and I'll just rewrite that value, the 77.75 over here. Once I get my pen back. Okay. Oops, that's 0.75, isn't it? Okay. So now we substitute in, so we're over here for B. We substitute in, and we say Z equals, oops, okay, Z equals, we have our mean, which is 868.86, and we subtract out this population mean of 1,225.15. Okay. Now notice that our sample mean is less than our population mean, so we know that our z-score is going to be negative. And we divide that by 77.75. So if we subtract this out, we work it out, you can try the calculations yourself, then we find that our value is negative 4.58, I think. Yes, so Z is equal to negative 4.58. Now these next two parts are asking us about why we think this is so big. This is a pretty extreme score. So if we looked ahead, remember we're talking about this distribution of means, right? It's less extreme in this direction. But if we're talking about looking at a negative 4.5, it's going to be out here somewhere well beyond the edge of our screen. Okay. Oops. All right, so it's going to be way over here. So why do we think that maybe it's so large? Well, probably because the underlying distribution is not normal. That distribution of scores, right? We have this distribution of scores here. It's probably not normal. It's probably skewed. There's probably a few really expensive houses up here. And the other thing, if we go back, is that for part D, why would we still then be able to use this normal curve percentages for the Z distribution, even though the underlying data are likely not distributed, so again, are normally distributed? Well, it's because of the central limit theorem. Which says that even if the underlying distribution of scores is skewed, the distribution of means will still be normal. So we're still able to use what we know about this distribution of means for computing the Z statistic. So remember, a z-statistic has to do with this distribution of means. A z-score has to do with an individual score compared to a sample mean. So that's my explanation for the Chapter 6, Question 42. I hope that helps clarify some things for you. And, oh, wrong direction. And so if you want another video like this for future homework problems, just let me know and I'd be happy to make one.